Shiwali Mohan. I'm a senior member of research staff at the Palo Alto Research Center, and I'm very excited today to be presenting the ongoing research we are doing on the DARPA Gala program at PARC. This is joint work with Matt Klenk, who's also an audience and is the program chair, as well as some other colleagues from PARC. All right, so a lot of members of this community and the audience would be very familiar with Common Model of Cognition paper that came out in 2017, written by John Laird, Christian LeBeer, and Paul Rosenblum. And the paper sort of goes over three cognitive architectures, SOAR, ACTAR, and Sigma. It describes the progress that has been made in the past 40 years and tries to distill the common elements of these architectures. These architectures are prominent not only in cognitive modeling, but also in intelligent agent design. And most recently, Michigan group has put SOAR on interactive task learning robot called Rosie, and can do amazing things. So the common elements of the common model of cognition are on a schematic on the right, and basically the way it works is the perception module will bring in some state information to working memory. Working memory with procedural memory rules will apply to working memory, drive behavior. At some point, there's going to be an action which is sent out to the motor module. And a lot of, especially in SOAR, a lot of the research has really focused on procedural knowledge, which is knowledge of how. And oftentimes we hand engineer all the rules that drive complex behavior, but then there's also significant body of work that goes on how these rules can be learned. So we have explanation-based learning, or chunking as it's called in SOAR, and that work has looked at how do you learn action models, preconditions, effects using EDL. SOAR also has reinforcement learning that helps learn new kinds of procedures, the value functions that go with them. And the commitment in SOAR is to perform a wide range of tasks. But in 2017, in the same collection and the same volume, another article came out by Hendricks and Forbes, who questioned, well, the procedural parts are really awesome, but what about the declarative knowledge? Like what about the conceptual knowledge in CMC? And their argument was that CMC focuses exclusively on problem solving, decision making, and behavior. On the other hand, human intelligence, one of the hallmarks of human intelligence is to build rich conceptual structures of the world, which is what CMC architectures would call knowledge of the what. So one way to sort of think about this dichotomy in knowledge is that if you think about Tara Fanoi, the goal state is declarative knowledge. This is the knowledge of what is it that we're trying to achieve. And you can achieve this goal by doing research, planning, reinforcement learning, and that's the knowledge of how to do that. Right? So Hendricks and Forbes highlight that a lot of the research in CMC architectures is on how to do things, but very little on what to do, or what does the how do we learn a declarative knowledge. So that sort of sets up the context for our research. We wanted to explore concept formation and use in CMC architecture. I'm most familiar with SOAR. This is what I was trained on, so we're using that to study concept learning and formation. And this work is a little bit different from what I've done previously and what James Kirk and Aaron Menninger have done. So we have previously used declarative knowledge represented in language and then translated and grounded into symbols that are coming from the perception and motor modules. And that's how we learn declarative knowledge. But in the paper, we explain how we can learn declarative knowledge from paired scene and language examples, right? So it's going two different ways you could acquire declarative knowledge. We want to incorporate models of analogical processing from companions. So this would they have explored using SME and SAGE. And the reason we want to use models of analogical processing is because there's a big body of work that says, like, this is how you can learn spatial concepts, physical reasoning, active state recognition, and things like that. And finally, which I think the main point that sets our work on concept formation apart from previous threads on concept formation in cognitive systems community is that we embed the problem of concept formation within larger cognitive concepts, right? The first one is embodied language processing. So if you're learning concepts, it should be, that knowledge should be useful in understanding language in embodied agents. And we have previously published some of the ELP work at ACS, and I will make sure to highlight how this third work connects to this previous work. And then even a bigger, larger cognitive concept is ITL, interactive task learning. And the hypothesis behind this research area is that you need to be able to program robots through natural means. Language is one of the ways in which you could program robots. And so we are exploring how concept learning can support task execution and action in the environment. And because we are part of the cognitive systems community, I really have a meta goal, which is to really solve the debate between soul and companions. Like there's a lot of argument back and forth between the communities. And to me, both architectures have their real strengths. And I think a real common model of cognition would be try to put these pieces together into something that can do things very cool. All right, so I'm a big fan of implemented systems. So we have implemented a system called AILEEN. It's Advanced Cognitive Learning for Embodied Language. Again, the acronym doesn't really go with the name, but that's what it is. The AILEEN agent belongs to the Rosie family of cognitive systems. It's just a bit cooler and more stylish because we have deep learning systems embedded into it. So we have a robot. Robot looks, there's a camera that looks over the robot. The camera image comes out, then we have a YOLO computer vision module that will extract out bounding boxes and centroids. It would extract out some percepts, shapes, and colors. And then all of those, the bounding box and centroids go into a qualitative reasoning module that will extract qualitative symbols out of the relationship between objects. So you could think of things like disconnect, O1 and O2 are disconnected. All of that information goes into source, or does its reasoning and all kinds of awesome metacognitive processing. Eventually comes out with an action. The action is then converted into control signals through inverse kinematics. What this paper really talks about is how we connect a new kind of memory called concept memory with SOAR. There's a grammar learning component that we are not going to go into for this talk. All right, so now to the best part about my talk, something that I'm very excited about, the video. So this is the environment that the AILEEN agent is working on. There's a tabletop that's a camera on the top of it. So you can, AILEEN can see its environment from the top. We can see it from all different sides. This window is the interaction between an instructor and an AILEEN agent. So the agent learns through a process that we call guided participation, in which an instructor would introduce different concepts to AILEEN, and AILEEN is supposed to learn from it, and the instructor will gradually increase the complexity of
Shiwali, we're not seeing the video right now.
Are you seeing the window?
We see the slide, we see the AILEEN demo slide, but we do not see, we just see a white screen underneath it.
Ooh. How about now?
We can see it.
Okay. All right. So yeah, sorry about that. This is the environment window. AILEEN looks at the tabletop on the top. There's a camera placed on the top, which is not visible here. There's the instructor and AILEEN interaction will go on in the bottom right corner, and this is source processing. A lot of operators are going to fire, and one of the reasons I put it here is because this is sort of like the white box way of learning things, where you break down each learning step into different processing steps. And what that allows you to do is this really cool metacognitive reasoning about learning, that you actually are reasoning about how much you know and don't know, and that drives interaction. So let's start with the first thing the instructor says. We have to verify if there is a cone. And AILEEN starts with no knowledge at this point, goes through its processing, and it can say, well, you know, it's a fail. I don't know anything. I can't see. I can't interpret. I don't recognize anything that can be interpreted as cone. So now what the instructor can do is to try to teach AILEEN. Like once you know the agent doesn't know anything, you can try to introduce concepts to AILEEN. So the instructor can say, well, inform green cone, so you're supposed to learn from it. AILEEN will go through its own instruction processing module, and then it will come back with a response. And all of this, basically what AILEEN is doing is it's like, I have seen 2 new words. I don't know what each of these are. So let me try to create new concepts for each word. So I have a concept for green, I have a concept for cone, and let me try to extract examples from the scene and try to learn from those concepts. The instructor can keep on, and notice that all of this is online, and it just run. So you can keep on introducing new things to AILEEN. Sometimes it learns, sometimes it fails, but the behavior just keeps on happening. The instructor also taught blue cone. And this is another interesting thing, that it could recognize that the only new concept here was blue, right? The cone was an original concept, so it can transfer some of that knowledge to the new scene, and then starts learning about blue. Once you have put in a few examples of cones in there, you can actually ask it to do the verify task again. So you can say, well, can you see it? Can you verify a cone? Are you seeing a cone in the environment? And this is another interesting thing, that AILEEN has never seen the red boxes that are over here, right? And everything is red, right? But it can still has enough knowledge to say, well, I do see a cone. So that's interesting. You don't need to know the entire problem space or the knowledge space before you start acting. You can start to do useful things with very partial knowledge as well. So now it's just going to go through several object learning experiences. So we'll just keep on placing different objects in front of it and teach the agent new things. So now you can, once you have taught it a few different objects, you can start going towards a little bit more complex concepts like spatial concepts. So here we are the instructor tries to see if the agent can recognize that the red cylinder is right of the green cylinder. Because it's the first time AILEEN is seeing this, there's going to be a failure. And then you can try to, once it fails, you can try to teach it, right? So you can, again, introduce new kinds of, you can just say, well, try to learn from this example. Another interesting thing that you can do is you can use language to then guide attention to different parts, right? So we are trying to say, well, blue cone is to the right of the red cylinder, and we're trying to learn from it. And there's another cone, a distractor object, but you're saying, well, you have to focus on these objects and these relationships. So note that all of this knowledge was learned from previous interactions, and now we can use it to then guide attention to the specific part. We can see, so we can introduce new kinds of concepts. And then eventually what you can do is to actually do action. So the instructor can demonstrate a trace of an action. So here the instructor is saying, move the move the blue cylinder to the right of the red cylinder. We give it a different example. So if the instructor is actually moving the arm of the robot to do those actions. And then AILEEN can learn from these traces and then plan the action for itself. So right now we are asking AILEEN to move the green cube to the right of the red cube. And here AILEEN is just going to do the task. And now note that all of these different components of knowledge that we had learned online through interaction can all be composed together to do action planning in a physical spatial domain. All right, so going back to my talk, how does this really work? So let's just start with, are you seeing my slides?
Yes, we can see your slide.
Okay, so AILEEN has some knowledge about that the word cylinder actually maps to a perceptual symbol called cylinder. The way it would use it is instructor would say verify cylinder, it goes into an interaction processing module, creates a goal for itself, which is where you have to verify that the linguistic verb goes with the scene. Then you go into a comprehension step. The comprehension step has three different processes in it. So first you parse, you know that a cylinder is a noun type object. That means what you're trying to do is establish an object reference. Then you map. So you go from the linguistic verb word cylinder to a perceptual symbol that's coming in through your visual module. And once you can map this, you know that cylinder actually means CV cylinder. You can create grounds for the specific reference. So you can say, okay, this must mean that the object O2 is referred to through the word cylinder. You can say, because there's at least one object that you identified on the scene, you come back and you say, tell the instructor that I found it. The instructor can give you a good score. So this is a new sort of instruction process that we introduced in the paper. But what happens when AILEEN doesn't know, right? So there's no knowledge of how does the word map to different parts of its reasoning and perception. In that case, AILEEN is going to fail. So you're failed at the mapping step. You don't know what cylinder is. And then you can go into the learning steps and then try to put more examples into learning. For this, so you can assume that the way AILEEN learns from specific to general. So the first hypothesis it's going to create about the concept cylinder is that it has to be both red and cylinder. And what then will do is if you showed it a green cylinder, it's just going to fail, but it's going to fail at a different step. And then you can learn again, you can start putting more examples into it and help it generalize. So that's sort of how our the current work fits into how AILEEN and Rosie typically function. So diving right into concept memory design, the paper describes a set of desiderata. For what a concept memory should be, it should be architecturally integrated. We want to use relational representations because they give us a lot of robustness and strength and generalizability. It should be able to learn and represent diverse types of concepts. So in the paper, we talk about how to learn visual concepts. So these are concepts that go with words like red, blue, the shapes and size words. We want to learn spatial concepts, which is relationships between objects. So this would be like right off, up, above, in front of, and actions, which is move something to the right? So we want to be able to have single memory, single algorithm that can learn these different types of objects. We want to learn from examples and not through instruction. We want to show incremental accumulation of knowledge. So you should be able to operate with partial knowledge, do the best you can, and then gather. And as more knowledge appears, you start expanding on what you know. You want to facilitate diverse reasoning. So you not only want to recognize something happening or recognize objects, but you actually want to be able to act in the environment. So whatever concept representations you're using and whatever you're learning from, you should be able to act with that knowledge. So that's the sort of the cool thing we showed, where you observe someone do a set of actions in the environment, and then you sort of can transfer it and then do the action yourself. And we want to learn from human little supervision because we're trying to learn from human scale of examples, from the number of examples that are plausible for a human to give. So not hundreds, not even tens, but few. Okay. So when we extract examples from experience, this is how it looks like. This is an example for red. It's represented in a predicate calculus representation. So you would know that O1 is a type of, is detected as red, detected as a cube, and then you can infer that it belongs to the concept R red. Spatial concepts are a little bit more complex because you also have objects and their attributes and descriptions. You may have some relational symbols that have been extracted from the qualitative module, and then you want to infer this symbol that you want to infer that something is to the right of the other. Action concepts are even more complex. Here we are trying to use the holds and predicate. So we are saying, well, at time t0, this is what the state was, and then you want to describe all temporal changes through this. Through this representation, we are also explicitly encoding that T1 comes after T2 and T0 and T2 comes after T1. So basically, you are ordering your experiences in a temporal way. So I'm probably going to butcher the descriptions of SME. If I do, please blame Matt and complain to him. But this is how I understand it. So SME is a very cool theoretical framework to compare two different relational representations. Here is a representation. So for us, relations would be the top order nodes in this graph. Entities would be the next set of nodes, and then we have attributes. And what we want to do is if we have a base, that's the representation we want to match against, and we get a new sort of relational description of the current state, we will establish correspondences. We will say which facts are aligned with other facts. We will evaluate a max score. So that would be evaluating the quality of overlap between the base and the target. And if the quality is really good, if you can really match all of these elements together, you can actually infer certain things about the target, which may not be actually present. So that's analogical reasoning. And then what generalization does is that sometimes there's there's partial observability, there's noise. In our case, because of the embodiment, sometimes you're getting this curious things, right? So then I just can't show you the example for red. Anytime I show you the example of red, it has to be connected. It will be correlated with a shape symbol, right? And not correlated, right? It will come with a shape symbol. So you at some point you have to figure out which parts of the graph that you're matched against actually matter for your reasoning, and which parts are just sort of is just a product of your embodiment or spurious nature of your domain. So you try to generalize those parts away, and then you get generalization.
3 minutes.
All right. Yes. Okay, so this is how quickly this would work. We have 4 different methods or protocols with the concept memory. You try to create so here you're trying to create a generalization context, cylinder. Then you want to store examples in it. So you have the name of the generalization context. You want to store a graph. So here I want to say a red cylinder can be inferred as a cylinder. Then I can try to query what I know. So I send it the generalization context. I send it which graph I want to match this context against. And then as a cue, I give it an inference question. So I say, given this information about the scene, can you infer if any of these objects is a cylinder type object? And in this case, if the match, which is true here, the match score is going to be less than the match threshold. And then you will fail at this lookup. And this is how store will drive its reasoning, right? So once you fail, you can try to gather more examples and revise the concept. You can store more examples. And once you start storing more examples, you start seeing these kinds of generalization effects. So you generalize away the specific objects, and then you also start calculating the frequency of facts observed within the generalization context, and that leads to, so eventually you end up learning that the Shreve cylinder is what's correlated with the meaning of the word cylinder, and these other parts are just spurious. And this knowledge will grow incrementally. Let me just go into the evaluation framework, and I can come back to the action parts if there's time. Right. So one of the problems, some of the concerns, or at least the contributions I think of this paper is to propose a new kind of evaluation framework. And in my past few years of experience, I found that it's really hard to evaluate interactive cognitive systems. What kinds of metrics should we be reporting? What kinds of paradigms should we be using? So in this paper, we propose a new empirical framework. This is motivated by online learning methods like reinforcement learning. We want to benchmark what interactive concept learning looks like for 2 different types of concepts. And this is how the evaluation framework is set up. There are 3 different metrics that we are really interested in. First, we are trying to understand and measure how smart the agent is in picking out the right set of examples and storing them, right? So because an active learner should be able to figure out the examples that matter the most. Once you have put examples in your concept memory, you want to evaluate how much you generalize, right? So this we do by doing verification tests with distractors, as an example over here. So once you've learned a green cone, you can place green cone with different objects around it, and you can evaluate if it actually can recognize green cone. The second cause of concern is if what we are learning is over general. So if we showed that if we asked it to recognize a yellow box when it didn't exist, does it detect a yellow box? So these are the 3 things we care about. We try to do it in an interactive fashion. A trial is a sequence of inform, and then a generality exam and a specificity exam. So here are results from visual word learning. The bars on the X and the Y axis on the left is a number of examples the agent is storing in its concept memory. And you see that it's dropping down very quickly within tens of examples. As it's learning, as it's storing examples, you see its score on generality exam growing, and this is what is to be expected. And it very quickly grows again to the best performance possible. And then the specificity exam, so it doesn't ever recognize negative concepts, like negative examples, right? That's the quality of the concept recognition method drops. So this is really good. This is the results of visual word learning. Once you have started all the visual words, you can start teaching spatial words. And you can see the same sort of effect here as well, that the number of examples it's storing is dropping down, that the more examples, more experience you're giving it, the generality score grows, and the specificity score sort of stays stable. This is with action word learning. Here you are actually trying to do actions demonstrating actions for it. And here we are seeing a lot more noise, and this noise is interesting because the algorithms themselves should enable perfect action recognition in noise. The problem is sort of what we discovered is an instructor error. Once you start moving objects around, and sometimes you place them very close together, they just like push each other apart, and that causes some instruction error. So that's what that variability is from. I'm going to stop here with just some highlights of the paper, and thank you.
Thank you, Shiwali. I think we have time for a few questions. Here is a question from Chris McClellan.
Mm-hmm.
All of your learning seems to be impasse-driven learning. Is AILEEN able to do impasse-free learning?
So the motivation behind impasse-driven learning is coming from SOAR architecture, that when you realize where you lack knowledge, that is where the knowledge sort of needs to be revised and repaired and fixed, right? So that's what the motivation is. The impasse-free learning, I think, may make an appearance when the instructor sort of gives you feedback and says, well, no, you were wrong. And then that way that is some more signal of that, the knowledge that you had at that point was wrong and you want to fix it. So that's how I would think about impasse-free learning. I'm not completely sure what you mean by it, but that's how I would think that there's some other supervision about the...
Well, since I'm here, I might as well. Like kind of unsupervised stuff. So like if you see a bunch of things that, learning like a general concept for different variations of a cone, because,
Right, I see. So we are exploring different ways to get that supervision from. So one is just task usage. So if you can successfully use concepts and tasks, you know that your representation of those concepts was pretty solid, right? So you can reinforce that. The other thing is more exploratory learning, which is also something we are exploring, where the agent is just motivated to, look at different objects, reassemble them, and things like that. So just trying to build more concepts. We're exploring both parts, but I think it would still fit into the impasse-driven learning framework, as in that the information that you lack knowledge comes from, the task that you're trying to do, that forces an impact and that causes you to learn.
Okay, this question is from Ifra Idris. In case of failure, is there a way for the system to learn new concepts without the explicit information provided by the instructor?
You could try to explore. We haven't really gone down that path too much. It would be really hard because the set of potential hypotheses is very big. And to us, learning from social interactions is very motivating because that's how humans learn, and that simplifies your learning problem, right? So if you have an instructor, if you assume someone who's giving you specific examples and is really motivated and invested in teaching you, you can rely on that sort of instinct of humans to teach people, right? It's a pretty natural experience. So that's what we want to really leverage, is to have the instructor either simplify your environment or give you specific examples to learn your concepts from. And then it's your job, the agent's job, to generalize that knowledge to different scenes, right? So that's what a lot of our motivation is coming from. If we go after this other paradigm of just completely unsupervised learning, I believe we will go down the same path of doing this with a lot more data, because that's what you would need to then invalidate some of the hypotheses that are not there.
Okay, I think we have time for one other quick question. This again is so you're getting lots of repeat questions from Chris McLean and Ifra Idris, and you probably want to connect with them later. This one is from Chris. Currently, the AILEEN architecture has separate memories for episodic, semantic, and conceptual knowledge. Do you have any thoughts about how these different memories might be integrated?
Oh, I actually have a lot of thoughts about this. So the way the concept memory functions is basically it has episodes, right? You're storing specific examples, and then it's trying to combine all of them together into a more general sort of what's called G-pool and SAGE. So that's more semantic knowledge, right? And these specific examples on the scene are more episodic knowledge. So what we propose as concept memory is actually a bridge between source episodic and semantic. And right now we're just characterizing the functional properties of it, but at some point there would be an architecture integration that would try to bring the context-specific knowledge and then extract out general semantics from it. And hopefully we can figure out a way to do it with an algorithm like SME and SAGE.
Good. I think we'll have to stop here. Thank